And I'm going to do a new share. Okay. So 59 is similar to the question you were asking about.
Is that in chapter 7?
This is in chapter 6.
What page is it on?
It's on page 306.
Oh,
But
it's
in my email, I said that you would have to account for the greater number of protons in the nucleus.
okay. Yeah, right.
Okay, so here the formula you can see is the electron is negative z squared RHC over n squared, where z is the number of protons in the nucleus essentially.
Okay.
So if this were a hydrogen atom, z would be 1 and 1 squared is 1, so you have your normal formula, correct?
Right.
But helium has 2 protons in the nucleus, so you would use 4
Okay.
times the, and then if you did lithium or beryllium, you would do 9 and 16 respectively.
But it can only be used with the ions that have 1 electron, right?
Yeah.
Okay. All right. And that's just for the energy. So there's no way to really calculate the radius because there's a different number of protons.
Right.
Okay.
And you would presume that the radius would be smaller for a helium ion, but you'd expect the radius to be larger for a lithium or a, well, I should take that back. You expect the radius of the 1s electron to be smaller for a lithium and for beryllium and so forth and so on, if we're looking at a 1s electron. But if you're looking at the outermost shell electron, you'd expect the radius to be larger.
Right.
And the reason you would expect the radius to be smaller for a 1s electron for lithium than say for helium is because they're both first shell electrons, and lithium has 3 protons, helium only has 2. The reason you would expect the shell to be larger for an outer shell electron on lithium is because it's in the second shell, not the first. So this kind of answers the problem, the kind of question you have. You'd use z squared.
Okay. And then negative, is that within parentheses of the z or outside?
That's outside because z is always a positive number. It's the atomic number.
Okay.
And the
then-
energy of the electron will always be negative because that's how much energy it releases when it lands on the atom.
Okay.
Okay?
Yep. Thank you.
You bet. All right, where do we go from here?
I have a question.
Go ahead.
Problem 51 from chapter 8.
51 from chapter 8.
So it's a bond dissociation problem like we were doing earlier.
Okay.
Do
Do you have a page for that?
405.
Thank you.
The answer I calculated is wrong based off of the book's answer for the bond dissociation enthalpy, but I did it correctly with the enthalpy of reaction. I got the same answer, but I don't know why my math was off on the first part.
Well, let's take a look here. So number 51, we have the reaction of H2C, CH2, gas plus H2O. Gas gives us what looks like ethanol. And we're doing the heat of reaction based on the bonds being broken and the bonds being made, right?
Mhm.
So we're going to do the sum of the bonds broken minus the sum of the bonds made. And here we use the D to represent the bond dissociation energy. Okay, and the reason it's minus the bonds made is because of when you break them, you had to put energy in, that's positive. When you make bonds, energy is released, and that's negative. Okay, so to do this problem, you have to have a Lewis structure. If you don't have a Lewis structure, you're not able to do it. So here's the Lewis structure for ethene. Here's the Lewis structure for water. And here's the Lewis structure for ethanol. So when we take a look at the bonds that are going to be broken, we take a look here at these, and there's going to be 4 carbon-hydrogen bonds. So this is 4 times the dissociation energy for every carbon-hydrogen bond, because there are 4 of them, 1, 2, 3, 4, plus 1 bond dissociation energy for a carbon-carbon double bond, plus 2 times the bond dissociation energy for an oxygen-hydrogen single bond. So those are all the bonds that we're breaking.
Okay, I know what I did already.
Well, let me go ahead and finish writing out the rest of this just so that people can see that.
Okay.
So minus, we have 1, 2, 3, 4, 5 bond dissociation energies of carbon, hydrogen, plus 1 bond dissociation energy for carbon, carbon. I've run out of room, plus 1 bond dissociation energy carbon, oxygen, plus 1 to the bond dissociation energy of oxygen, hydrogen. And which one of these bond dissociation energies are you supposed to memorize?
None.
What's that?
None of them.
Yeah, none of them. You look them up in the book. So Rebecca, do you want me to finish this one?
No, I don't need you to. I do have a question though.
Okay, go ahead.
Not specifically about this one, but if the reaction, let's say you gave us the reactants or whatever, something we could come up with a product of, you still need to balance it. And then each one would, when you balance it, if the coefficients are, 2 or 3, anything but 1, you draw the Lewis structure. When you draw the Lewis structure, do you draw 2 of them as well?
Well, I usually do because that allows me to count more easily. So if we did something like this, these are the Lewis structures, right? So I could do it one of 2 ways. I could say there's 2 hydrogen-hydrogen single bonds because of that 2 there, or I could just draw them both out and just count them, 1, 2.
Right. Okay.
So I'm in the habit of writing them out so I can just count them 1, 2, 3, 4.
Unless if it's huge or something.
It's a Tony Proust strategy where sometimes Tony forgets the coefficients. So if I draw them out, I don't forget.
So Hess's law, enthalpy of reaction and bond dissociation enthalpy, same thing.
Well, if you're calculating the heat of a reaction, yeah.
Okay.
Yeah, there are different ways of getting to the heat of reaction. And when you do those different methods for the same reaction, you don't always get the same answer.
Oh, yeah.
But they're close to one another.
Okay.
Why aren't they always the same, Charlotte?
The model.
Because they're models, and models are not perfect, but they're supposed to get you close.
Right.
Okay.
Charlotte and I were talking about that earlier today. You'll see that posted later when I wake up from my nap.
While we're on the subject, I did number 52,
Uh-huh.
but I want to know if I did it right. Because
Is
Well,
this
I
the
don't-
one that I did in class or on a lecture or something?
I'm not sure.
So for this one,
My answers aren't the same. I'm getting one positive and one negative.
did you do the right subtraction? Remember,
Yeah.
let's take a look real quick. We'll just do the setup, okay?
Mhm.
Okay, so for this one, I thought we did do this one.
We did. We did 50.
You said 52, right?
Yeah.
Okay, so the first setup
Oh.
is this. Hang on.
Hmm.
We're going to do the bond dissociation energies first. So here, D, we want to put broken, right?
Yeah.
And then minus E or epsilon, D, formed or made. So here, this is going to be reactants, and this is going to be products. So you're going to get, for those that are broken, we're going to have 8 carbon-hydrogen bonds. And here, I just didn't want to write this twice because I didn't really have enough room. Here are 4 carbon-hydrogen bonds, but because of the 2, I actually have 8. Plus 1 oxygen-oxygen double bond. And then the ones that are formed are 1, 2, 3, 3 carbon-hydrogen single bonds, 1 carbon-oxygen single bond, and 1 oxygen-hydrogen single bond. And so a carbon-hydrogen single bond is
413.
413. Oxygen-oxygen double is what? 498.
Oh. See, I got that wrong.
Did you use the single bond energy?
I don't know, because the value I had was 745.
745. You used the carbon-oxygen double bond.
Oh, I did. And that's how I wrote it too.
Yeah, well, so there's your mistake. I guess it just happened to be chance that you got the opposite number, the same number, but the opposite sign.
Hmm.
So that's actually an easier problem to fix, right?
Yeah.
Okay, so this is how it looks this way. And my ish would be roughly 3,300 plus 500
Don't we have
minus,
two
what's that?
Don't we have 2 moles of methanol?
Oh,
So,
thank you. So 6 of them here
okay.
and 2 of them here and 2 of them here. So this would be minus 2,400. So we'll call that 2,500, 700, and 900. Yeah, we did do this one. I'm almost sure of it. So this is 4,800 or 3,800 here, and this is like 4,100. So negative 300-ish is what we would expect.
Okay.
This is the one where
Yeah.
we did it as a liquid and we did it as a gas.
Oh, okay.
And the one as a liquid ended up being closer to the bond dissociation energy. Or I should say the bond dissociation energy method using a liquid here ended up being closer to the enthalpies of formation method, which seemed unusual. And if I remember right, this was what, minus 320
Yeah.
kilojoules
Yeah.
with only two significant figures because of the way things add together.
Yeah.
And that is for 2 moles of CH4, which would be the same as minus 160 kilojoules per 1 mole of CH4. Yeah, it's all coming back to me now. And I believe when we did this using some of the enthalpy of formation of the products minus the enthalpy of formation of the reactants. This is where we kind of did it backwards, but the products would be the CH3OH. And that value was like minus 300 or something, if I remember right.
What page is the appendix on?
It's like 40.
Wait.
30.
Oh.
So here we had 2 times minus 277. And then 2 times negative 74.87 kilojoules plus 0, because it takes no energy to make O2 from its standard state. Liquid, gas, gas. And I think this one ended up being minus 327.4 kilojoules or something like that. This is ish. Let's see. Actually, I think I had a better number than that. Nope. 277.0.
So you looked up the value for methanol, right?
Right, and it's minus 277. Oh,
So ethanol.
actually, I picked the wrong one. That's ethanol.
Okay.
It's minus 238.4.
Wait. Where do you? It's not 201. Negative 201. Methanol. CH308.
No, methanol is minus 238.4 because it's a liquid.
Oh. Oh man. Okay.
Not, but we did do 201.0 when we said, let's pretend it's a gas.
Right. Okay.
And we get 327.06 kilojoules, which becomes negative 327.1 kilojoules. So did you use a wrong number again for this one?
Yep.
No, wait, this is the same one we were talking about before. You didn't use 498, right? You used 745 or something like that, or?
Yeah. And then with the second part, I used the gas value.
201.
Yeah.
Okay,
Okay.
so I can see a way to trick people on the test is to give you enthalpies of formation for the gases and liquids of stuff.
I thought you said you don't make the test to trick us.
What's that?
I thought you said you don't make the test in such a way to trick us.
Well, it's not a trick. You're supposed to pick the right thing.
It's on recording, Charlotte.
Yeah, you just said trick. That's not nice.
No, it's not a trick. I'm saying it's not a trick. You just have to pick the right thing.
Okay, Tony.
At least we're aware now, yeah.
Yeah.
So then how would we know something like
Hang on a second there. Just hold your horses there. I thought I heard Wisconsin or something in there.
in my voice?
Yeah.
I'm from Vermont originally.
Okay, East Coast. You have that little thing that goes on from the East Coast, or from that area. Can you say moon for us?
Moon.
Yeah, a little bit in there.
I lived in the Midwest a long time too. I've got a lot of different accents.
Okay. I just got the Tony accent, which is kind of slur everything I say. All right. Go ahead with your question, Rebecca.
So, I know the state of the reactants there, but the state of the product, knowing that it's a liquid, not a gas, how do we, for the lower one, to get the right number? Because you said you could, quote unquote, trick us that way.
Well, you see here, this is the gas and this is the liquid.
Right.
You just have to pick the right one.
And so we're not going to be predicting products or anything. You'll give us the reaction.
Now you're trying to tie me down into questions. I don't know. I mean, yeah, I could say, here's the reaction, figure out what the products are.
Okay.
I mean, it would be totally legit for me to say, you react methane plus oxygen, write a balanced reaction, write out the Lewis structures, draw the molecular geometries, give me bond angles.
Mhm.
I mean, you could make the whole exam about one problem. You know what I mean?
Right.
So, and then I could even, heck, I could even say, and if you ended up with 5 grams when you started with 20 here, what's your percent yield? I mean, there's all sorts of things I could do with one problem.
Right.
I tend not to do that because if you screw up one part of the problem, you might screw up all of it.
Mhm.
So I tend to compartmentalize different aspects.
Okay, that's good.
So in answer to your question, yeah, I could do anything I want. I mean, as long as it's reasonable.
Mhm.
And it is reasonable for you guys to figure out, not that this would be the product, but I could ask you, what are the combustion products? So what are the combustion products of this?
CO2 gas,
And
H2 gas.
H2O,
Oh, H2O liquid. Yeah, that's right.
right? And so,
Yeah.
you know, I could then ask you for the Lewis structure. Well, here, they didn't even ask for the Lewis structures. They said, calculate the enthalpy of a reaction using bond association energies. And you have to get the Lewis structures before you do that.
Mhm.
So, you know, I could do that with a reaction like that, where it's predictive products. And
I guess that was my question then, to know whether or not it was the just CO2 plus H2O, like a normal combustion reaction, or the methanol, or what that was.
this is not a combustion reaction. This is a redox reaction. How do I know it's a redox reaction?
O2?
O2 on what in the reaction.
Okay.
So the oxidation number on oxygen here is 0. The oxidation number here is -2. Since the oxidation number of oxygen is changing, it's a redox. And guess what oxygen is? It's the oxidizing agent,
Right, okay.
which means it's getting reduced.
Mhm.
If it's getting reduced, it's getting rigged, which means it's doing what?
Gain of electrons.
Gaining electrons. And if it's 0 here and -2 here, isn't it gaining electrons?
Yes.
Yep.
Okay,
See how much we've learned so far?
we have.
And I saw Charlotte. Charlotte's actually shaking her head like, yeah, I get it. Yeah, I remember. Yeah.
There's been a lot.
Yes. So did I answer your question, Rebecca?
Yes, you did. Thank you.
Okay. I just don't want to make you feel like I wasn't trying to answer. So what else can I help you with?
We could do more problems in the back.
Your choice. What problems would you like me to do? You want me to just pick some?
Well, Charlotte, what do you feel like you struggle with the most? For me, I feel like it's what we were just doing, the enthalpy.
Yeah, the
For
new.
me, it's staying awake.
But you know, practice is good either way for anything.
Okay, so here we have some problems. When you see one that looks good, let me know. What's the answer to this one? Which ones are capable of forming hypervalent compounds without picking each and every one out? What's the answer?
7A's.
Period
Nope.
below.
Anything in period 3, 4, 5, 6, or 7.
Oh, okay.
B, E, G, H.
Draw Lewis structures, we can do that. Draw Lewis structures, we can do that. Possible resonance structures, we can do that. So you guys probably have a pretty good hand on structures, right?
Yeah.
So here's one. The reason I'm picking this one is just because we can answer a few questions without doing too much work. So this is the molecule urea. It's a very interesting molecule. It's excreted by humans. So this is a living molecule, as it were. And back in the day, people thought that only living organisms could make molecules that came from living organisms. This was the first living molecule, as it were, that was synthesized in a bottle. And basically, a person took carbon dioxide and nitrogen and made urea. And that's when people realized that, oh, you know what? Just because it comes from a living organism doesn't mean that it can't come from a non-living thing or source. Okay, which bonds are polar and which are non-polar? So here, when you're asked a question like this, they don't really mean kind of polar. They mean, is it polar or non-polar? Meaning, are the electronegativities different?
Right.
So is the carbon, hydrogen, nitrogen bond polar?
Yeah.
Yes. Nitrogen is like a 3O, hydrogen's a 2-1.
Right.
How about nitrogen carbon? Yes,
Yeah.
because nitrogen's like a 3O and carbon's a 2-5. How about the carbon oxygen?
Yeah.
Yes. So basically, what types of bonds are not polar in an absolute sense? And the answer is when the two atoms bonded together are identical. So a carbon-carbon bond is nonpolar. A hydrogen-hydrogen bond is nonpolar. Are you guys with me there?
Yeah.
Okay. Which is the most polar bond in the molecule? And the answer is going to be the oxygen-carbon, because carbon is a 2-5, oxygen's a 3-5, and it's a difference of 1.
Mm-hmm.
The difference between nitrogen and hydrogen, nitrogen is a 3-0, hydrogen's a 2-1, the difference is 0.9. So it's not quite as polar.
Okay.
And the difference between carbon and nitrogen is going to be 0.5. Okay, so for the most polar bond, which is the carbon-oxygen, which atom is the negative end of the bond dipole? Oxygen. Why?
More electronegative.
More electronegative. Okay, this is an interesting one that can be done fairly quickly. Considering both formal charge and bond polarity, predict on which atom or atoms the positive charge resides in the following. So H3O plus has 8 electrons, and so this is what it looks like. So that's the Lewis structure. And to predict which atom the positive charge resides on, you assign formal charges. So where does the positive charge reside?
Oxygen.
On oxygen, because it's got the formal charge of +1.
Okay.
Okay, so that's how you do a problem like this. So that being said, we'll move on. So resonance structures, we've done that. Isoelectronic. What does isoelectronic mean? Well, let's take a look at these two compounds, BO3 2 minus and CO3 2 minus, I'm sorry, and BO3 3 minus. So CO3 2 minus has 4 electrons plus 3 times 6 plus 2 for a total of 24 electrons. BO3 3 minus has 3 plus 3 times 6 plus 3 for 24 electrons. So isoelectronic means they have the same number of valence electrons, but they're also arranged around the atoms in the same way.
Mm.
So here's what CO3 looks like. "24 electrons. And here's what BO3 looks like. Now, the reason I'm drawing it this way is because boron can make 3 bonds, and we know that, right?
Yeah.
Here, we've got a -1, -1, -1, and a plus, or excuse me, and a 0 formal charge. But we could also do this. Now here we would have a -1, -1, 0, and a +1. Nope, -1.
Mhm.
Okay, so which of these two is better? Why is the top? I agree. Why is the top one better?
Because of the electroneutrality principle.
So can you give me a little bit more than just saying because the electroneutrality principle?
Okay, because the formal charges add up to the charge of the compound of the ion.
They do in both cases though, -1, -1, -1.
Is it because the negatives are on the more electronegative element?
Right. This negative on the boron is not as good as this negative on the oxygen.
But technically, are there 3 different recursions for these?
There are, but I only drew one each.
Right.
So here, I would argue that you might argue that they are. If you consider this guy here, they look very similar. So if this one ended up being very important, then I would say, yeah, they are not resonance, isoelectronic. And in fact, here's the dealio. This guy has 3 of them, right? That look like this and this, right? Without drawing them all out.
Right.
The more resonance structures you have, the more stable it is. Because with the resonance structures, you're spreading out charge. So I'd say that they are isoelectronic. So that was the first question. Whoops, there we go. Are they isoelectronic? How many resonance structures does each ion have? Here, I'd say it has 3. Here, I'd say 4. Now, why does this one have an extra resonance structure compared to this one? And the answer is really simple. Boron can make 3 bonds. Carbon doesn't. Boron can also make 4 bonds. Okay. What are the formal charges on each atom in these ions? We already did that. Here, we didn't do it. It's a 0, -1, -1, and a 0. If an H+ ion attaches to the carbonate to form the bicarbonate ion, does it attach to an O atom or to the carbon atom? So if we wanted to add an H+, where are we going to put it? And the obvious answer is on one of the oxygens that has a negative charge. Where do you think the next hydrogen would add?
On the next -1 charge oxygen?
Yeah. So here, this +1 is attracted to this -1, and that's why this happens. And this is why we have those oxyanions or oxoanions. Hydrogen ends up attaching to them. And when hydrogen attaches to them, it could also release. So that's why these things are acids. H2CO3, H2SO4. The hydrogens are bonded to oxygens. Okay, so that's an interesting question. Yeah, this is just like the other one. Okay, considering the following, in which compound are the bonds most polar? Which compounds are not polar? Are the hydrogen atoms in NH2Cl negative or positive? So this is one we can do. So let's draw the Lewis structure for each of these. For A, without going through all of the steps, this is what you're going to get. For B, you're going to get this. For C, you're going to get this. Why don't we make a double bond to boron here with one of the fluorines so that boron would have an octet and 4 bonds?
It prefers 3 bonds.
Because boron can make 3 bonds. Plus, if you look at the formal charges here, they end up being 0 everywhere. So this is the best structure. So D, this is carbon disulfide. Okay. In which compounds are the bonds most polar? Well, I do want you to remember fluorine, oxygen, nitrogen, carbon, beryllium, boron, and lithium. And they are 4O, 3,5, 3O, 2,5, 2O, 1,5, and 1O. And then I want you to know hydrogen, which is 2,1. So what is the difference in electronegativities between a carbon and a hydrogen? It's 0.4. Nitrogen and a hydrogen is 0.9. Chlorine, you would have to look it up. Chlorine is a 3O. So nitrogen and chlorine is a 0. Boron and a fluorine, you can see, is 2.5. Carbon and a sulfur, I don't know what sulfur is, but it's below oxygen, and it's got to be smaller than chlorine, so it's probably a 2.8. So here, it's probably a difference of about 0.3. So in answer to the question, in which compound are the bonds most polar? Right here, most polar bonds. And you can almost make a bet on it that the most polar bonds are going to be found in the molecule with the most electronegative atom, okay?
Yeah.
Mhm.
Which compounds are not polar? Well, this guy is not polar because when you draw it in 3 dimensions, the most electronegative atom is not on one side. This one, I would say, is polar.
B.
Because here, if we draw it this way, we can definitely cut this in half, and the most electronegative atom, oh, I'm sorry, chlorine and nitrogen are the same. So this one, you could say that it's slightly polar because the nitrogen and chlorine are more polar than the hydrogens. So let me redraw that. So here, if I cut this like this, I got a more electronegative side, more electropositive. So I put that down for the polarity for that guy. This guy's trigonal planar. And the most electronegative atom is fluorine. Is the fluorine on one side of this molecule? Can we cut this in 2 and get all the fluorines on one side? Not a chance. So this is nonpolar. Sometimes I like to do these problems using your vector way of doing it there, Charlotte. Okay, so here, 3 vectors, right?
Yeah.
But with my vectors, I call it walking the dog. So here's the deal. That boron is a person walking 3 dogs.
Yeah.
It's walking 3 big dogs, like German Shepherds or, you know, Pyrenees, whatever, big dogs, because it's the most electronegative atom. These dogs are pulling on the dog walker in those directions in which you see the arrows. So which way would this whole ensemble move if all the dogs are equal and pulling in opposite directions? It wouldn't move at all, right? So it's nonpolar. So let's see walking the dog applied another way. Now, iodine is much less polar than fluorine. So you're the dog walker, and you got these two big German shepherds pulling you this way, and you got this one little chihuahua that probably is pulling you in the opposite direction just slightly. Which way are you going to go? You're going to go in that direction, right? Because the two German shepherds are going to drag you and the chihuahua in that direction. But it's going to be between the two arrows together, right?
Yeah.
So that's what's going to happen. So walking the dog. And in some case, you're being chased by the dog. And that would be when the arrows go in the opposite direction. Okay, how about this one? Non-polar, right? Okay, are the H atoms in NH2Cl negative or positive? Well, I would say that they all have zero formal charges, so they're neither.
Mm.
Fair enough?
Is it asking about like the polarity though in comparison?
Oh, if they're asking that, then I would say that they're slightly positive, right?
Mhm.
Because this is a 3-0 and this is a 2-1.
Yeah.
Okay. So we've already done one like this. We're going to skip this one. Give the bond order for the following molecules.
You can do it, huh?
I was just looking for some paper. So CN is going to look like this. So what's the bond order in this guy?
3.
3. How about this guy? What are the bond orders? And the answers are, there's a CH with a bond order of 1. There's a CC with a bond order of 1. And there's a C triple bond N, which is a bond order of 3.
Right.
SO3 looks like this. No resonance structures, because every atom here is a formal charge of 0. So what's the bond order?
2.
Okay, for this guy here, we've got CH3, CH, double bond C, and then H2. So what's the bond order for a CH?
1.
What's the bond order for a CC?
1.5.
1. This doesn't have any resonance.
Oh, okay.
How about for the C double bond C?
That's what I was getting confused. I was adding the C single bond and the double bond and then dividing by 2.
You only do that when you have resonance structures.
Yeah, okay.
And we don't have any here.
Yeah.
These are all zeros, by the way, also. So when all of your formal charges are 0, you don't have resonance structures.
Right.
Okay. Predict which is shorter. How about A?
No.
SiO. Why is that? Well, I'm going to show you. Carbon, nitrogen, oxygen, fluorine. Carbon, nitrogen, oxygen, fluorine. They get smaller as you go to the right, correct?
Right.
Okay.
So oxygen will be smaller than nitrogen. So a silicon oxygen bond should be shorter.
Mm-hmm.
Because if this is silicon and this is nitrogen and this is silicon and this is oxygen, this length is smaller than this length. So this is oxygen, this is nitrogen. So this is the shorter one because silicon is the same in each, but oxygen is smaller than nitrogen. Fair enough?
Yeah.
How about SiO or CO? Well,
CO
here, oxygen is the same. So which one's smaller, carbon or silicon?
Carbon.
Yeah, goes this way. Here's carbon. So silicon would be like that. They just get bigger as you go down. So for B, we would expect CO to be smaller bond, shorter bond. How about CF and CBr? Well, if there's F, what is chlorine going to look like?
Really small.
Bigger, right?
Yeah,
Yeah.
bromine even bigger.
And then what is bromine going to look like?
Larger than that even.
Yeah,
So
and so-
CF smallest.
Whoops, I should make it bigger. And so we basically have what looks like a snowman, don't we? Charlotte, have you ever lived anywhere where there was snow?
No.
Have you ever made a snowman?
Maybe.
Well, you're not going to make any if you move to Texas.
I know. That's
Oh
okay.
no, that's far away.
Yeah, but Rebecca, if you've lived in Vermont, you've made your fair share of snowmen.
Oh yeah,
And you probably made your fair share of snow angels too, right?
all of the above. Jump off the top of the roof and on your house into the snow. There's so much.
How far was the roof?
Not so far.
1 story, 2 stories?
Yeah, it was a ranch kind of house. It's actually really cool. The house I lived in out there was built in 1760.
Wow. Before the Revolutionary War, huh?
It was a very old house, all kinds of relics, old farmers' almanacs from the 1700s. There was a barn attached to the house with a giant hayloft and all these rigging from ships, you know, because it's pretty close to the Atlantic.
Wow, that sounds really cool.
It was pretty bad in a good way.
Okay. I used to jump off the roof into snow all the time because I actually spent a month shoveling snow off of roofs for a job.
Wow, that's hard work. It's dangerous.
Yep, that was in North Lake Tahoe.
Wow.
And the neatest thing about the job was that you get like 5 feet of snow on the roofs, and they put plastic on the roofs, like garbage bag plastic. But there'd be strips where there'd be no plastic, so that would hold the snow on the roofs. And then you would go and dig down to the place where they didn't have plastic, and the whole big old 5-foot deep slab of snow would slide down the roof onto the ground below. And if there was a car down there, it would have been crushed.
Yeah.
But the cool thing about the job was you would dig down, but be on top of the snow so that when it cut loose, you'd ride it down to the edge of the roof. And you were tied in by a rope to your belt on your waist. And so you'd be caught at the last second.
Wow.
And one time I did this and I heard this rip. And I was like, holy schmoly. Turned out I had tied not into my belt, but I tied into my belt loop of my pants. And the belt loop didn't break, not one bit. It held me up. And it was a pair of Levi corduroy pants.
Wow.
No one would have expected a belt loop to hold back a person, but it held me back. But I
Oh,
also,
what year was this?
what's that?
What year was this? Pants used to be made a little more sturdier.
Before you were born.
Right? The old Levi's are pretty hardcore though. You
Yeah.
know? They're sturdy.
It wasn't in the 1800s. It was probably like 82, 1982. So older than you guys. But I also weighed a lot less. It'd probably break now. Okay, so which is shorter? The carbon-nitrogen bond, the carbon-nitrogen triple bond? Which one of these?
Triple
So here,
bond.
notice they have the carbon-nitrogen bond or carbon-nitrogen triple bond in this. So maybe it would be interesting to draw this. So here we have a nitrogen with two hydrogens bonded to a carbon, which is also bonded to two hydrogens, bonded to a carbon and triple bonded to a nitrogen. So which one is shorter?
The triple bond with the carbon and nitrogen.
Right, because more electrons means more rubber bands pulling the atoms together. So it's going to be shorter.
Right.
Fair enough?
Mm-hmm.
Okay, here, compare the nitrogen-nitrogen bond in hydrazine with that in laughing gas. So hydrazine with this H2N, this is what we would predict for it. And in laughing gas, we would end up with this. Why is nitrogen the central atom in laughing gas?
To make more bonds.
Makes more bonds. So we're looking at 16 electrons. So here's 16 electrons. This is a -1, this is a +1. This does have some resonance. So here, this would be a 0, +1, and a -1. Why do we think the resonance structure on the left is more important?
Because the negative is on the more electronegative.
Right. And in this resonance structure, what is this bond order equal to?
In the first one,
Yep,
just 3.
3. And what is this nitrogen-nitrogen bond order equal to?
2.
2. So what is the average nitrogen-nitrogen bond order?
1.5 or 2.5.
2.5. So this is where we're going to look at two resonance structures and average them.
Yeah.
And notice I'm not averaging 3 + 1 and saying 2.
Mm-hmm.
I'm averaging 3 and 2 because those are the same bonds between the same two atoms. And here, the BO is 1, and here, the BO is 2. So the average NOBO is 1.5. Okay, so they want to know which one is shorter. This one here, which is a 2.5, or this one here, which is a BO of 1, right?
Right.
So which one is shorter?
The single nitrogen.
No, that's longer.
Oh yeah. The shortest one's the triple bond.
That's
Usually,
right.
always.
Well, we don't want to call it a triple. We're going to say it's a 2.5.
Yeah.
So this one's shorter.
Because if you were comparing two that had resonant structures and they both had 3, you would and they didn't have the same average bond order, that's how you'd choose.
Yeah, well, there could be another molecule we could probably draw where in one molecule there's a nitrogen-nitrogen double bond. And actually, I'm going to be honest, it's going to be hard to come up with a molecule that has a nitrogen-nitrogen triple and a nitrogen-nitrogen double versus a double and a single, because nitrogen doesn't make single bonds
Mm-hmm.
in resonance structures. So, But yeah, if your average was smaller for two resonance structures, you go with that being the longer bond. And if the average was larger, that would be the shorter bond. Okay. Which one is stronger?
Still the shortest one, yeah?
Yep. Because here you're actually breaking 2.5 bonds versus one bond.
So it's always really easy then to remove the hydrogen, relatively.
Yeah, compared to other atoms, you bet. Okay. Okay, so here's one of the type you guys were talking about. Using bond association enthalpies, estimate the enthalpy change for this reaction. So I think we'll stop after this one, if that's okay.
Okay.
So if
Yep.
we're going to do this, maybe we start off with the equation. The equation looks like this. And when we say bonds broken, that would be in the reactants, right?
Mhm.
And bonds made would be in the products. So that's a really good start to this problem. The next thing we do is probably draw out the Lewis structures. Okay. So let's look at the bonds broken. We have one bond dissociation energy for a carbon-oxygen triple bond. We have one bond dissociation energy for a chlorine-chlorine single bond. So those are ones broken. And the ones being made would be negative 2 bond dissociation energies for a chlorine-carbon single bond, and 1 bond dissociation energy for a carbon-oxygen double bond. Okay. So I have not memorized these bond dissociation energies. I'm sure there are some chemist out there that has memorized a bunch of these, but it's not me. Okay, so can you see down here, we have a carbon-carbon triple bond at 1046.
Mhm.
Okay. So I'm going to put 1046 kilojoules because 1 times 1046 is 1046. Chlorine, chlorine, here's a chlorine. And here's the chlorine at 242. Chlorine, carbon. Here's a carbon. And here's a chlorine, 339. And then we have a carbon-oxygen double bond. And you see that we have actually a choice. Here's a carbon-oxygen bond in CO2, which is 803. And here's a carbon-oxygen double bond, which is 745. And I think that's the one we want to use because we're not looking at CO2, correct?
Right. Just CO.
So we're going to do plus 745 kilojoules. So I'm always going to do an ish. If I add these two numbers together, I get roughly 1300-ish, right?
Yeah.
And 2 times 339 is roughly 640. And 640 plus 745 is roughly, I don't know, 1400-ish.
Mhm.
So I expect it'll be around minus 100-ish kilojoules. So let's find out what it is. Where's my calculator? Oh. So 1046 plus 242 minus 745, then minus 3 times 339. Oh, 2 times. So I get minus 135.
Yeah, that's what I got.
I didn't get that. What did you do?
Did
You
you
didn't-
add inside
did.
the brackets first?
What's that?
Mistakes. Let me see.
So the 1046 plus the 242 is 1288 kilojoules. And the 2 times 339 is 678. Then plus 745 is 1423 kilojoules. And I still get minus 135 kilojoules. Did you find your mistake, Charlotte?
Yeah.
Excellent. Are you going to do that again, like on a test?
Hopefully not.
Definitely not. Okay, so that's how you do that. So whenever you're doing the bond dissociation enthalpies, not only do you want the correct equation to use, here it is, but what else do you need?
The coefficients?
Yes, and what else?
You need.
Values.
Lewis structures.
Oh, okay, yeah.
You see, if I don't drive that into your brains, you're going to forget that.
Right.
Well, yeah, because it almost seems like you want to go back up to the formula, to the reaction, but you don't. You want to stick with the Lewis structures when you're multiplying.
Right. Well, when you're counting bonds being broken, you need to know what
Right.
bonds are there. And the formula helps you figure out what bonds are there, but having the Lewis structure is so much easier.
Well, the formula helps you find out how many of each, like how many you have to multiply it by.
Oh yeah, like here the 2O2 would be 2 oxygen double bonds.
Right.
Yep. And here, how many bonds would you break here?
It's not bonded.
0.
0 bonds, because there are no bonds.
Right.
This actually looks like an interesting one. Let's do it. So using this end bond dissociation enthalpy, estimate the bond dissociation enthalpy for an oxygen-oxygen bond in ozone. Okay, so here's ozone, O3, 18 electrons. So this is what we have, right? For
Yep.
ozone.
Those are the two different resonance structures.
Yep. And
Yep.
so what is the bond order here for one of these oxygen bonds when we average it? Average bond order is 1.5, right?
Mm-hmm.
And here it's a 1.5 also. But to do this problem, there are no bond dissociation energies for a 1.5 bond. So what we have to do is this. Whoops, my bad. We have to say that this is the reaction. So when we use this formula here, D bonds broken minus D bonds formed or made, we would say we're going to break one oxygen-oxygen single bond and one oxygen-oxygen double bond. That's what we would do.
Can you say that again?
We would say that we're breaking one oxygen-oxygen single bond and one oxygen-oxygen double bond because we have no 1.5 bond on our list.
Okay, great.
Okay, then we would do minus 2 times an oxygen-oxygen double bond.
Mm-hmm.
So this is on like page 405 or something like that. Nope, not 405. 392. So an oxygen-oxygen single is 146. An oxygen-oxygen double is 498, but that's in O2. But we're not given any other choice but to use that. So we're going to say 498. And then minus 2 times 498 kilojoules. So you can see, roughly speaking, that's about 1,000. And roughly speaking, that's about 650. So the difference should be about 350, right?
Yep.
And let's see what we get. And I get minus 352 kilojoules. Okay. So that's the change in energy for the reaction, minus 392, and we just calculated minus 352. So those are close. Now, it actually says estimate the bond association enthalpy for OO bond and ozone. So we're going to do this another way now. We're actually going to do this. So this is a given. We're going to estimate the bond association energy for OO in O3. So the bond's being broken. We're going to put 2 bond dissociation energies for OO in ozone minus 2 times the bond dissociation energy for O2. So I'm not sure if you follow that, but basically in this problem here, I'm saying that the amount of energy to break that bond is the same as the amount of energy to break that bond because of resonance.
Because they're technically the same length.
They're technically the same. They're both 1.5 bonds.
So that's why you did 2 instead of 1 times 1 single and then 1 plus 1 times the double.
Right. So this is where we treat them separately. We find out that, hey, it comes out kind of close, but now we're saying this is based on experimental evidence. Let's find out what it actually costs to break both of those bonds one at a time. So I'm going to call this 2x minus 2 times the bond association energy of oxygen. So X is what we're interested in.
Yeah, okay.
So now I get 2x is equal to the heat of reaction plus 2 times O2. And that's going to be minus 392 kilojoules plus 2 times 498 kilojoules. And that'll give us roughly, 2x is roughly 600.
Mm-hmm.
Let's see, 996 minus 392. So I get 604 kilojoules. So X is 302 kilojoules. And we know that a double bond is 498, right?
Right.
And a single bond is 146. If we kind of draw a number line here, 100, 200, 300, 400, 500. This is the oxygen-oxygen double bond. This is an oxygen-oxygen single bond. And this is the oxygen-oxygen bond in ozone, which we think has a bond order equal to 1.5. And so here, if this is a bond order of 2 and this is a bond order of 1, wow, look at that. That is kind of right down the middle between the two, isn't it?
Mm-hmm.
So that means that each of these bonds is pretty much the same. And they really are like 1.5 bonds. Yeah, I like that problem. Okay, sorry for keeping you, but that was a fun one. Okay, maybe I'll see you guys at 6
Thank you.
if you don't have lives.
Well, not approaching an exam, no.
Okay. All right. Thank you for calling in.
Thanks.
Thank you. Bye.